finally, we're going to look at Sn and what's known as the Cayley Theorem. All right, now the first few, or at least the first few definitions and stuff you should probably recognize. So definition one. So Sn, remember, is a set of all permutations on the numbers 1 through n. And An is the set consisting of all even permutations. By the way, An also has another name. It's called the alternating group. Get it? An, alternating group. Well, you probably should recall in class, I proved that An was a subgroup of Sn for n greater than or equal to 2. By the way, when n is equal to 1, we don't have any even permutations. We just have one element, and one element is the identity, right? All right, so how did this argument go? Well, we're going to proceed by the short criteria for subgroups. And if n is greater than or equal to 2, then I can write the identity as the transposition 1, 2 times itself, right? Well, since it's written as a product of an even number of transpositions, that's what it means to be an even permutation. It's an An. What have I just shown? That An is non-empty. Finally, I take two things in An, alpha 1 and alpha 2. I need to show alpha 1 times the inverse of alpha 2 happens to be an An. All right, but for alpha 1 and alpha 2 to be an An, that means I can write alpha 1 as what? A product of an even number of transpositions. So alpha 1 looks like gamma 1 times gamma 2 dot 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 gamma 2p, and I just call it 2p to remind you that that's even. By the same token, alpha 2 is a product delta 1 through delta 2q, where each of the deltas are also transpositions. All right, so now I look at this product, which I have to prove is in An. Well, what's the product? It's gamma 1, gamma 2, dot, 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 gamma 2p times the inverse of alpha 2, which is the inverse of that, right? But what's that? That is this, the first part. And how do I take inverses? I reverse the order and take inverses of each one. But now I notice that each of these deltas is a transposition. Well, a transposition is the cycle of length 2. It has order 2. It is its own inverse. So delta 2q inverse is just delta 2q. Delta 2q minus 1 inverse is just delta q minus 1 dot 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 down to delta n. So here's a product of transpositions. Here's a product of transpositions. I've written this as a product of transpositions. How many do I have? The answer is 2p add 2q. And 2p add 2q, I notice, is an even number. So I've written it as an even number of a product of transpositions. That's what it means to be in An. All right. Now, the next few things I'm going to leave up to you for homework. Show that Sn minus An, that is the set of all odd permutations, is not a subgroup. Tell me something it violates. Theorem 4, I believe I proved in class. I'm going to leave that as an exercise for you to repeat. Here's a map, phi sub g. So fix g in big G. And my map, phi sub g, is multiplication by g. And what do I claim? That this map is a permutation on the set G. All right, so prove that. What's a permutation? A bijective map going from the set to itself. So prove this is a bijective map going from G into G, right? I'm going to leave theorem 5 for you to prove as well. I believe I did that in class, but look things up. The cardinality of the alternating group I claim is n factorial over 2. And my hint is, recall that the cardinality of Sn is n factorial. So what am I saying? Half the elements are in An, and the other half are not. In other words, half the elements of Sn are even permutations and half are odd permutations. That's my hint, right? Find me a bijective map going from the set of even permutations to the set of odd permutations. Now the odd permutations are what? Sn not An. If you find a bijective map going from there to there, then you've shown me this. And again, I claim I've done that. But I want to see you repeat the argument. All right. Finally, as promised, I want to prove Cayley's theorem. What does Cayley's theorem say? It says every finite group is isomorphic to a subgroup of Sn. That is why Sn is so important for sum n. And it turns out that sum n is the cardinality of my group. All right, so Sn, if I understand it, I understand every finite group, because every finite group is a subgroup of Sn. All right, so let's see how the argument goes, right? Pick a group of order n. Then I'm going to claim, all right, well, if G has n things in it, then I can write it as G1, G2, ... Gn. Now, for each element in G sub j, I define this map, phi sub j. It goes from G to G. By phi sub j of G is just multiplication on the left by G sub j. Now, by theorem 4, which I've asked you to prove, this map is a permutation. All right, so each of these maps, phi sub j, which depends on G sub j, is a permutation. What's Sn, by the way? It's the set of all permutations over the set 1 through n. Well, so I claim that I can think of the set 1 through n as the same as my set big G if I just identify G1 with its index 1, G2 with its index 2, ... G sub n with its index n. All right, so each of these phi sub j's is a permutation. Now I'm going to define a map, F, going from G, that's this set, to Sn, the set of all permutations on G. What is my map? F of an element G sub j goes to this homomorphism, actually permutation, phi sub j. All right, so there's my map that goes from my set G, which is a group, into the set Sn, which is the set of all permutations on n things. Now, what am I going to claim? I claim that F is injective. And I also claim it's a homomorphism. So let's prove the first one, that F is injective. All right, so F starts with G, so suppose F of GK equals F of GJ. Well, F goes to a permutation phi of j. So what does this mean? That means that the permutation phi of k is the same as a permutation phi of j. Now those are maps going from G to G. Okay, so what does it mean for phi of k to be the same as phi of j? It means that if I take phi of k and I plug in any g, I get the same thing as when I take phi of j and plug in any g. But phi sub k of g is just gk times that g, just like phi sub j of g is just gj times that same g. Well, but I'm in a group, and I have therefore right cancellation, so I can cancel those g's, and I get g of k equals g of j, and I'm done, right? I suppose f of garbage is f of garbage, and I show the garbage has to be the same. Claim 2. Now I claim that this map F is a homomorphism. All right, now to be a homomorphism, it's got to preserve the binary operations. The binary operation here is multiplication in G. The binary operation here is function composition of these phi sub j's. So I look at f of gk gj times gj of g, that map, lots of g's, is what? Well, it's just multiplication by this element, right? So it's gk gj of g. But I could write that like this by associativity. And what is gj times g? Well, that's the map phi sub g of j, right? Because phi sub j of g is just g sub j. So it's phi sub j of g, right? Maybe I said it wrong the other way, but now I've got it. Yes? All right, so this is phi sub k composed with phi sub j, because that's what function composition does. So what I've shown is that phi of gk times g sub j is in fact phi sub k composed with phi sub j. What I've shown is it respects the binary operation in both sets. All right, so what do I have now? An injective homomorphism. But if I notice that any map, if I go from G to its image, right, to the only thing it hits, that image is a subset of Sn. Yes? Well, if I just look at the map from G to its image, it's automatically surjective because the only thing I'm looking at is what it hits. So the map going from G to the image of F is surjective, it is a homomorphism, it is injective. Therefore, it is a bijective homomorphism, which is an isomorphism. All right, so F going from G to the image of F is an isomorphism. What does that say? G is isomorphic to the image of F. But furthermore, since G is a group, and we know what? That the image of a subgroup is a group, or is a subgroup in the big set, then I know that the image of F is a subgroup of Sn. Therefore, G is isomorphic to an image of F, which is a subgroup of Sn, and I am done. All right, so I think I'm going to stop there. And then for homework, I believe I'm going to assign exercise 11, 12, and